A single Boolean flag inside a function seems harmless. But what if I told you that flag is actually a hidden state machine, one that grows exponentially with every flag you add, silently multiplying your test scenarios and your bugs? By the end of this video, you'll see why. We reach for a Boolean flag because it feels like the simplest possible addition. A function that takes an include underscore an active parameter and branches, if true, include everything, if false, only active records. 2 lines of code, job done. It looks clean. But under the hood, that's not one function anymore. It's 2 different behaviors welded together behind a tiny toggle. Edsger Dijkstra argued that we need formal symbols that prevent us from writing nonsense, because the apparent naturalness of code can mask its absurdity. A Boolean parameter seems like a harmless binary option, but in fact, it is a state selector that widens the interface. Dijkstra also pointed out that narrow interfaces are vital because changing an interface can multiply the work on both sides, sometimes drastically. That single flag becomes an interface expansion with immediate, measurable cost. Each call site must now choose between 2 paths, and every developer reading the code must mentally unpack the branching. Moreover, the cyclomatic complexity of the function instantly jumps. With a single flag, you have 2 possible execution paths. Add a second flag and you have 4, 3 flags give 8 paths. In general, n Boolean flags create 2 to the power of n distinct logical flows. Each path demands separate tests, and if you miss one, you ship a bug. The interactions between flags produce a hidden state explosion that we'll examine. That's why a simple flag is never just a flag, it's a microstate machine. Now add a second flag, is underscore admin and is underscore verified. Suddenly, you're not just combining 2 independent toggles, you're constructing a small state machine. The function now has 4 possible combined states: admin verified, admin unverified, non-admin verified, non-admin unverified. If some combinations are invalid, say, an unverified admin shouldn't exist, your code must enforce that, but the type system does nothing to help. This is reminiscent of Carhor's billion-dollar mistake with null pointers. You're forcing callers to check preconditions without any compiler guarantee. Hoare later called his invention a billion-dollar mistake, because null references require the user to check before using. A nullable Boolean, bool, in C# takes this further by allowing 3 values, true, false, or null. That null communicates no value or undecided, turning a simple toggle into a 3-way fork. With 2 nullable Booleans, you now have 3 squared equals 9 distinct states, each a potential path through your logic. The hidden state machine expands silently, and your test matrix balloons from 4 cases to 9, and that's before adding more flags. You rely on the caller to avoid impossible states, but nothing in the type system prevents them. The implicit complexity multiplies without a single loud complaint from the compiler. Thus, from 2 innocuous flags, you've built a machine that quietly demands 9 test cases, each hiding a potential bug. This unchecked explosion mirrors a famous episode in programming language history, ALGOL 68. Designed in 1968, the language committee loaded it with features, overly general constructs, non-standard terminology, and a definition spanning hundreds of pages. The result? Implementing a compiler became so difficult that the language effectively had 0 implementations and 0 users. Hoare and Dijkstra themselves criticized ALGOL 68 for abandoning the simplicity of ALGOL 60 and turning into a vehicle for complex, overly general ideas. Many later languages, like Pascal and Ada, were direct reactions against this complexity, selectively picking features while discarding the unwieldy whole. Your Boolean-laden function follows the same pattern. Each flag adds a degree of freedom that interacts with every other, causing state explosion. Just as ALGOL 68's complexity made it practically unbuildable, a handful of Booleans can make your codebase mental model collapse under its own combinatorial weight. That's why the language was said to have no implementations and no users. The parallel is striking. Every Boolean flag you add is like an extra, poorly specified language feature that multiplies the implementation surface. The cost isn't just academic, it's real, measured in debugging hours and fragile testing. The ALGOL 68 episode warns us that state explosion is not a theoretical concern, it's an engineering failure mode. The nullable Boolean sharpens the problem. In C#, bool is a value type that admits true, false, or null. That third state often maps to a no-op or a deferred action, effectively turning a function into a three-state automaton. Consider a method process order, bool. Has paid. If true, charge the customer; if false, cancel the order; if null, wait for payment. This is a state machine with transitions, waiting paid or cancelled. But the code likely hides those states behind a series of if-else checks without an explicit model. Carhor's null references, the billion-dollar mistake, force the same kind of defensive code, but here the null is used as a legitimate business value, not just in absence. When you combine multiple nullable flags, the state space jumps to 3 to the power of n. For just 2 nullable Booleans, you have 9 possible states, 4 3, 27. Your test matrix explodes, and the implicit machine becomes nearly impossible to reason about. Yet many developers treat nullable Booleans like any other Boolean, unaware of the extra dimension they introduce. So ask yourself, does this Boolean really have only 2 meaningful states, or have I smuggled in a third? So what should you reach for instead? Not every Boolean needs replacing; a single flag sometimes is the clearest choice. But when you see multiple Booleans or nullable Booleans, consider replacing them with a dedicated type. A simple enum with named states like order status.pending payment, paid, cancelled makes the state machine explicit. The compiler can then check exhaustiveness, ensuring every path is handled. In functional languages, some types provide similar safety. In object-oriented code, you might use a state pattern or sealed classes. Dijkstra's advice on narrow interfaces points to the real solution: don't transmit a loose bag of flags that force the receiver to reconstruct state. Instead, send a precise, self-contained message. Sometimes the best fix is not a richer type but splitting the function into 2 each with a single responsibility and no ambiguous toggles. By narrowing the interface, you shrink the state explosion curve from exponential to linear, from hidden to visible. The cost of wider interfaces isn't just more code, it's the compounding tax on testing, debugging, and future change. Keep your interfaces narrow, and your Booleans will serve you, not betray you. Remember, the goal isn't to eliminate Booleans but to ensure they don't accidentally become a state matrix. Booleans aren't bad. They are precise bits of yes or no. But when they stack up or become nullable, they morph into implicit state machines that quietly expand the complexity of your system. By recognizing the interface width problem and borrowing lessons from